All right, so equilibrium is perhaps one of the most important concepts in chemistry, and here we are at the end of the year covering it. If some of you guys decide to go on to AP Chemistry, you'll find that equilibrium is a great big part of chemistry at the college level. Why? Because most reactions that occur are in equilibrium. So what does that mean? Target 16.1. I can explain what is meant by a system in equilibrium. So up until now, equations that we've looked at have always had just one arrow. Okay? Like NaCl, we say dissolves to form Na plus and Cl minus. Problem is that it's like you as a 2-year-old going up to your parents and asking them, where do babies come from? The odds are that they're probably not going to get very specific. Why? Because they don't want you to be traumatized at the grand old age of 2. In the same way, earlier on in the school year, I didn't want you to be traumatized with equilibrium. Not that it's hard, because I think you're going to find that it's actually pretty easy. But it was just going to complicate what was already a difficult concept. I didn't want to add another layer to it. The fact is, most reactions will only go so far, and then they reach equilibrium. Okay? They'll only go so far, and then they reach equilibrium. There are 4 possibilities. Okay? I like to think of this, well, okay, there are just 4 possibilities, and then I'll give you a metaphor to help you understand later on. First possibility. Here's a reaction that will go until it's finished. Done. Yay! Okay? That's what you thought all reactions did. And I was, of course, lying to you or fibbing or not telling you the complete truth, whatever you want to believe. Here's a possibility where it'll go, almost used up, go, almost used up, bam! It's like it hits a wall. You thought you were going to go all the way for a touchdown, and then you get to the 10-yard line, and you are now going back and forth, back and forth, back and forth. Okay? That would be like sodium chloride. Sodium chloride will dissolve to a certain extent. It's like Stefan running with the ball. 10, 20, 30, 40, 50, 40, 30, 20. He's going to go all the way. And at the 15-yard line, he stops and goes, no, he doesn't trip. He stops and goes, I am rather indecisive as to whether I want to score now. And then he starts going in a circle at the 15-yard line. Okay? The first reaction, he goes all the way for a touchdown. Yes? Okay. Thank you. That's when he was playing football. Here's another reaction. It's the kickoff. He gets the ball at the end zone, and he runs to the 10-yard line, and at the 10-yard line, he becomes indecisive. Okay, and he just starts spinning around until somebody goes and annihilates him. All right? This is a situation like lead-2 chloride, where we said, hey, lead-2 chloride doesn't dissolve. Well, no, actually it does dissolve. But it just gets to the 15-yard line, and then it starts going back and forth. And to us, we simply can't see that enough of it has dissolved for us to think, hey, it dissolved. No, to us it appears as if it didn't dissolve. And finally, using our illustration, this would be Stefan running to the 10, to the 20, 30, 40, and he gets to midfield, and he stops and becomes indecisive and can't decide whether he wants to go backwards or forwards, backwards or forwards, backwards or forwards, until he gets tackled at the 50-yard line. So this is a system in perfect equilibrium. So it'll go only about halfway there and then reach equilibrium. Now, what is the problem? I can explain what an equilibrium constant is and what it can tell you about a system in equilibrium. What is the problem with using arrows in order to help us understand how far Stefan runs with the ball? Yeah, I mean, really, can you judge from how long the arrow is as to whether he goes to the 45 or the 50 or the opponent's 40? Or, how big is big? It's not quantitative. Arrows are just simply not very useful. So what we do is we come up with an equilibrium constant. An equilibrium constant gives us numbers that we can use to help us understand how far he goes before he gets indecisive. How far he goes before he gets indecisive. And remember, when he becomes indecisive, he just flitters back and forth between reactants and products. Reactants do their thing, products come back together to form reactants again. So it's as if the reaction has stopped, but you know it continues to go. But there's no net gain anymore. Equilibrium constant is measured by using the concentrations, molarities, of reactants and products in a balanced equation. So this is it. This is it. It is K equals the concentration of product C to the power. What power? To the power of its coefficient. So its coefficient goes there. The big number. The number that we use to balance equations. Go there. And then the concentrations go in the brackets. Remember what I told you, that anytime you see anything in brackets, the units inside are molarities. Molarity. So whenever you see a number in a bracket, it doesn't have to give you what the unit is. It's molarity, moles per liter. It's molarity. So the big letters in this equation refer to the concentrations of the ion or gas C, ion or gas D, ion or gas A, and B. And did you notice who's on top? The reactants or the products? Products over reactants. Products over reactants. Notice something else that I've told you. Folks, you can only determine the concentration of two things. Ions dissolved in water and gases dissolved in other gases. So only AQs and Gs are involved in these K values. Only AQs and Gs. Remember, the little numbers refer to the coefficients. K value, in essence, is a ratio. It is a ratio of products to reactants. So putting it simply, and this is one of my fibs, but it helps you understand. Putting it simply, if the K is a 5, that tells you you have 5 times as much product as reactants when it reaches equilibrium. If the K is 55, that means you have 55 times more products than reactants when it finally reaches equilibrium. What does that mean? K equals 5. Probably, if this is the 50-yard line on the football field, Stefan goes to maybe the 40. 55, Stefan goes deep, deep, deep into the opponent's field before he's finally tackled. So, if the K is 1, he reaches the 50-yard line. Why? What does that tell you? It tells you that you are halfway there to completing the reaction when he decides that he has become indecisive. That's kind of a funny way of saying that. He decides that he has become indecisive. Okay, so he catches the ball, He's running, gets to the 50-yard line, goes, I don't know if I want to continue. Maybe I should, maybe I shouldn't, maybe I should, maybe I shouldn't. That's K equals 1. We say that it is, that's K equals 1. So K is greater than 1, is product favored. K equals 1 is neither. And how far does he go if K is less than 1? Yep. A small decimal will get you here. A really, really small decimal will get you, he gets tackled back there. Okay? Look at it this way. Because this is actually, K values are very, very practical. A chemical engineer may be asked to make some sulfur dioxide, but there are 5 reactions that give you sulfur dioxide. Which one should he use? Yeah. What if I was to tell you that reaction number 1 has a K value of 0.035? Bad idea. What about 25 for number 2? 5 for number 3. 0.000023 for number 4. Use that one, maybe? Yeah. How about 562 for number 5? Number 5. Yeah. So a chemical engineer would look at their K values, and also he would have to take into consideration, because keep in mind that number 5 may be the most efficient of all these reactions, but what if the reactants are really expensive? So he has to balance how expensive the reactants are with the K value in order to get that. Because there might be a case where this is the most efficient reaction because the reactants are cheap. The reactants are cheap. I've even heard of cases where this is the most efficient because all the other reactions, the reactants are very expensive. You would end up losing more money than you would get. Okay. Very important fact. Since only gases and ions can be measured in molarity, liquids and solids are not included. They're not part of the expression. They're not part of the equation. Don't put down zeros for them because that does terrible things to the equation. Put down a 1 or nothing at all. Put down a 1 or nothing at all. Here's another metaphor to help you understand. If you get a business, most business models will tell you that that first year, your K value is going to be less than 1. Is that right? No. Less than?
Yeah, right.
First one was right.
No.
It's been a while since I've used the alligator. Less than 1. Okay? In other words, that first year, you will lose more money than you make. Okay? You're hoping by your second or third year for your K value to be 1. What does that mean? That means you are making as much money as you're losing. You're breaking even, which is actually a huge, huge point in the life of any job, any business. And then you're hoping by year 3 that your K value is greater than 1. Because what does that mean? That means that you are making more money. Now, you don't want your K value to be 2 or 3 or 5.6. Why? What does that mean? That means you're not making much more. You want your K values to be 300, because that means you're making far more money than you're spending. Okay? Does that help? I hope so. That's all I got. All right. So, Alec would like to do number 1. These are really easy, Alec. First of all, you start with K equals. Then it's products over reactants. Make sure that you only include those things that are AQs or Gs for gas. Go.
So, CO.
Where? In the denominator or numerator?
Alright, denominator.
Hold on. Let me remind you of something. See that? C goes on top. D goes on top. Okay. So what goes on top?
H2.
Brackets? Yes. Got to have it in brackets. H2 to the?
1.
Okay. Do you have to put a 1? No. Times?
Times CO2.
To the?
1.
Divided by?
CO.
To the?
1.
Times?
HOH.
To the?
1.
Are you sure? Are they all Gs or AQs?
Yes.
Okay. Done. That's it. You're done. You're done. That's how easy these things are. Yes.
Since this is an expression, we don't have to solve it.
Right. Tomorrow we'll add numbers to it. Yes. It's just algebra. It's just, yes. All right. Alec, pick somebody from that side of the room. Mark, go. How do we begin an expression? No, how do we begin the expression? K equals. Mr. Marino, what if you don't put K equals? It's wrong, actually, because it really doesn't mean anything. What? Okay, remember, it has to be in brackets. Very good. Did you notice? Where did that 2 come from? The coefficient. Lenoir, got a tough one to finish things up. Choose somebody over here. Grant. Go, Grant. How do we start?
K equals
Good start.
CO2.
Very nice. To the?
1.
Okay.
That's it.
He's right. That's it. But, okay. What did I say? Only G's and AQs are in effect here. But, what? No. That's it. This is a solid, and this is a solid. You're done. You're done. But, Mr. Marino, what happens if you have your only thing in the numerator and everything else is solid and dumb? Well, at that point, you may want to do that. Put a 1 over so there's no confusion. You don't want to say CO2, and that's an understood 1, Mr. Well, I get it that it's an understood 1, but that could lead to some confusion. So put 1 over CO2. You understand? All right, so we went over 3 targets. Hopefully now you have a good understanding of equilibrium. That's at whatever point that Stefan finally gets indecisive and his desire to go to the end zone. Okay? We talked about the importance of using numbers to help us understand how successful he's going to be. And then finally we set up the equation so that tomorrow we can come up with numbers.